Well, it is time to discuss about the modern atomic theory, and let's start the story with the Bohr model, because at that point it was pretty well known that the electrons move in orbits around the nucleus. Those orbits were elliptical, so we are picturing the atom like the solar system, where the nucleus is represented by the sun and the electrons would be the planets. However, there was a little problem with that, because if the electrons, which were moving really fast, if they were moving in those elliptic orbits, they will be releasing electromagnetic radiation. So what Bohr did was to incorporate some of the Planck's and Einstein's ideas to describe the atom, and then describe those electrons moving in those orbits as requiring energy to move between the orbits. Okay, so it's now those orbits will represent energy levels, and those electrons will be moving on those energy levels. And if they want to switch between orbits, then they will require energy, either to move to a higher level, or they have to release energy in order to move to a lower level. So this is pretty much what we are looking at. Okay, we have the nucleus here, and then we just number the orbits from 1 to infinity. And the lower or the larger the number, then means those electrons are farther away from the nucleus. Okay, so the main concept here is that those orbits will have a fixed energy associated with them. And electrons that have those just that amount of energy can move in that orbit. And if they are moving between orbits, they will, for example, if they are going from a higher energy level to a lower energy level, then they will release energy, and normally that energy will be released in the form of electromagnetic radiation or light. Okay, so this is what the Bohr model is saying. Those numbers that we are describing those orbits with is what we're going to call now the principal quantum number. So since the orbits are energy level, then this principal quantum number is describing the energy levels. Okay, the main energy level in which those electrons are moving in. Now, if we focus our attention in the hydrogen atom, then orbits, as we were describing, are now energy levels. And then these energy levels will, of course, increase in energy as they move away from the nucleus. So they require more energy to get farther away from the nucleus. Remember, those are electrons. The nucleus is positive. The nucleus is attracting the electrons. In order to put those electrons farther away from the nucleus, you have to provide energy. Okay? So this goes for the hydrogen atom. So this is the lowest energy level that the electrons. So that's the lowest energy level is how the closest those electrons can be to the nucleus, and that's what we call the ground state. Okay, the ground state. Let's remember this. This is the lowest energy level, and remember, when it comes to energy, those electrons want to be in the lowest energy possible. Okay, so lowest energy means more stability, and that's what the electrons want to be. And because the hydrogen atom only has one electron, the other energy levels is what we call excited states. Why excited states? Because you need to provide energy. Remember, it's just one electron, so if it's only one electron, that electron pretty much wants to be on the ground state, because it's the lowest energy level. In order to go to any of the other levels, you have to provide energy to that electron to go to those other levels, and therefore, because you are providing the energy, those becomes excited electronic states. Now, that interesting situation that happens with the hydrogen atom is that you can have any possible transition here. And by transition, I mean that electron moving between energy levels. So you can have every possibility. So you can start here in the ground level. Okay, here is the ground level. And you can go to any energy level. So you can go to the second energy level, third energy level, and you name it. And each one of those transitions will require a certain amount of energy. If you are going up, you have to add energy. If you are going down, you have to release energy. So that's pretty much the concept here. And what that originates is that since this is energy associated, and we are talking that that absorption of energy and releasing of energy is in the form of electromagnetic radiation, then we have the emission spectrum, okay, which is technically it's bright lines over a dark background, okay, because each one of those lines represents an energy transition. And because you are seeing bright lines over a dark background, then it means that a particular line is representing the energy that is being released when the electron is moving from one of those high energy levels to one of the low energy levels. Now, if you are going up, then you originate an absorption spectrum. Imagine that you are pointing a flashlight to a hydrogen atom, and then the hydrogen atom is using part of that light to move that electron to higher energy levels. Because it's absorbing energy, and remember, it will absorb a specific amount of energy. Just what's necessary to move to a higher energy level. Not more than that, not less than that. Okay, so that's why you see now you see here dark lines that represent the energy that is being absorbed by the electron to move to those higher energy levels. Okay, and I mean, because it is absorbing that energy, then it's no longer part of the spectrum because it was taken by that electron. Okay, and now notice that the position of the lines are the same. In one case, you are absorbing energy. In the other case, you are releasing the energy, but the amount of energy that is associated with that step, whether you are going up or going down, is going to be the same. Okay, so those energy levels are fixed. And it's a specific amount of energy that you will need to move between levels, either by releasing or by absorbing that amount of energy. If you are absorbing energy, you are originating an absorption spectrum. If you are releasing energy because you are going from higher to lower levels, you are originating a emission spectrum. Now, there is one way in which we can quantify that amount of energy. Okay, so technically, if we are talking about the energy of that electromagnetic radiation that is coming out of the electron if it's moving down, or that you have to provide to the electron if you're moving up, then that is the amount of energy that that photon has to have. And that amount of energy of the photon is equal to the difference in energy between those levels. Okay, and remember here, because we are talking about the photon, we are going to keep using our normal equations. Energy of the photon equals h nu, and you relate the frequency with the wavelength with the speed of light equation. Okay, so a simplified version of the previous diagram, we have energy levels 1 through 3, and here we have a transition between 1 and 3, and then another transition that goes from 3 to 2. So there is no limit in how the electron can move. The electron can do pretty much whatever it wants. The point is, to move up, you have to absorb energy. To move down, you have to release energy. That's pretty simple. So, but we can quantify that. And the way we quantify that is with the Rydberg equation. Okay, so this difference in energy is the difference in energy between the levels that electron is moving between. Okay, if it's going from 1 to 2, well, it's the difference in energy between levels 1 and 2. Okay, we have that Rydberg constant here, which is 2 0.18 10 to the negative 18 joules. And then we have the final energy level. And remember, this ends here. N is equal to 1, 2, 3, 4, whatever level you are moving between. Okay? Now, your book gives you two versions of the Rydberg equation. And since I don't want you to get confused about what equation to use, I want you to keep your eye on this one. Why this one? Because to me it makes a little more sense that if you're talking between transitions between energy levels, then you are calculating what the difference in energy between those levels are. Okay? And then most likely you will associate this energy with the energy of the photon. So pretty much here, the energy of the photon is going to be the absolute value of that difference in energy. Why? Because here we're gonna use the same concept that we saw in thermochemistry. If you are moving from a lower level to a higher level, you have to provide energy. That is an exothermic, that's an endothermic process, okay? The difference in energy has to be positive because you have to provide energy. And if you are moving from higher level to lower level, you have to release energy. So the process is exothermic, and therefore the sign of the changing energy has to be negative. Remember, the energy of the electron. This represents energy of the electron. But the energy of the photon always positive. Okay, so this is always positive. Okay, that's why we apply the absolute value of the difference in energy. So pay attention to what you are being asked. If we are asking for a difference in energy, then the sign matters. When you are moving to the energy of the photon, you will always use the positive value. And then with energy of the photon, then you use E equal h nu and C equal lambda nu, depending on what you have to do. But you already know these equations, right? You only need one more. And I don't want you to use the other one because it looks about the same, but the constant, the Rydberg constant, is different, has a different value. So again, if you are going to work with Rydberg equation, I would prefer that you use this one. However, you can do whatever you want. I just don't want you to get confused. So how do we use this equation? Okay, by the way, we can only use that for hydrogen. And well, pretty much in the exam, we are going to ask you just with hydrogen. We are not going to use this equation with any other element. And basically, the difference between other elements would be that the Rydberg constant will change. But there is nothing to learn with different elements that you cannot learn with just working with hydrogen. So, what is the changing energy of the electron in a hydrogen atom if the electron goes from a level 5 to level 3? So what is the data here? Okay, we are calculating delta E, right? And delta E is going to be equal to negative Rydberg constant times 1 over final level square minus 1 over initial level square. Now, which one is the final? The final level is actually 3. You are going to level 3, so that's the final destination. And your initial, your origin is level 5. So you are going from 5 to 3. So delta E is going to be minus 218 10 to the negative 18 joules times 1 over, finally is 3 square minus 1 over 5 square. Okay, and this is minus 155 10 to the negative 19 joules. So the difference in energy between level 5 and level 3 is 155 10 to the negative 19. Now this negative sign means it's an exothermic process. Therefore, energy is released. In order for that electron to go from level 5 to level 3, it has to release energy. How much? this much energy. Okay, this is going to come as the photon with energy equal to 155 10 to the negative 19. Okay, so it's pretty much natural to think, well, if you have that is the energy of the photon, well, what is the wavelength of that photon, right? So let's write that down again. So the energy of that photon is 155 10 to the negative 19 joules. Remember, since we are using energy of the photon, that's a positive value now. And we can use E equal h nu and C equal lambda nu. And as always, if we are working with all these variables and you want to go from energy to wavelength directly, we can cut the middleman here in frequency and just say that E is equal to hc over lambda. Remember, this is not exactly that you have to memorize that equation. You are just deriving that, and it's an easy derivation here. So you don't have to memorize it if you don't want to. So therefore, if we solve for wavelength here, then wavelength is going to be hc over E. And then we have our calculation, right? So h is Planck's constant, 6626, 10 to the negative 34 joules times second, times 3 10 to the power of 8 meters per second, and the energy is 155 10 to the negative 19 joules. So here joules cancel with joules, these seconds cancel with seconds, and you end up with meters. However, the question is asking for nanometers. If we're asking for nanometers, then we have to add another conversion factor here that is telling you that 1 nanometer is equal to 10 to the negative 19 nanometers. Sorry. No, that's not what I wanted. It's meters. 10 to the negative 19 meters. So meters cancel with meters. Now we end up with nanometers. Okay? So after you complete that calculation, lambda is going to be 1282 nanometers. Okay, so a photon with a wavelength of 1282 nanometers will be released when that atom goes from level 5 to level 3. Okay? So in the exam, we might ask you directly. We did it in 2 steps, and you're going to do 2 steps anyway. But here is the same question, just we are going directly for the wavelength. So here you are going now from level 3 to level 2. So first you have to calculate the difference in energy. And this is going to be minus 218, 10 to the negative 18 joules, times what is your final level. This is your final level, 2 squared. This is your initial level, 1 over 3 squared. The difference in energy is minus 303 10 to the negative 19. Remember, you are going from a higher level to a lower level, so the energy, the change in energy is negative. So the energy of the photon is the positive value, so it's 303 10 to the negative 19. And therefore, if the energy of the photon is hc over lambda, then lambda is going to be hc 6626 10 to the negative 34 joules times second times 3 10 to the power of 8 meters per second divided by the energy 303 10 to the negative 19. Joules go with joules, seconds with seconds, and then we need to convert these to nanometers. 1 nanometer is 10 to the negative 9 meters. And what we get here is 656 nanometers. Okay, so technically it's just a two-step calculation. I would say it's a rather simple calculation, but you have to make sure you know your equations. Okay, once again, you don't have to memorize this equation. If you use stepwise, first calculating frequency and then wavelength, that's fine. You're gonna get the same result, but at the end, it's up to you. So we've been talking about dual nature of the of matter and light for that matter as well. And one thing that since matter behaves as a particle and as a wave, then it's natural to think that matter, particles for that matter, will move in a wave-like behavior. So that means if you throw a ball, basically you should see the ball moving like a wave. Do you actually see that? Well, no, we don't see that. We are not able to see that, but it's happening whether you want to believe it or not. So how we describe that wave-like behavior of particles? Well, we have, technically this is what you would see, okay? So if that particle was moving in an orbit, then the particle should be moving like a wave in that orbit. And it has to be a whole number of waves that you have to have during that movement. You don't really have to worry too much about this, but in order to describe the wave-like behavior of matter, the wave-like behavior of particles, then we use the de Broglie equation. Now, this wavelength here, this is for particles, okay? Not light, not photons. Okay, so we are using here, that's the wavelength of the particle, right? So you have, this refers to the particle, and remember, a photon doesn't have a mass, so we cannot use this equation with a photon. Okay, so this is to describe if that particle is moving like a wave, then that will give you what is the wavelength in which that particle is moving. Okay, anything that is not a photon, you can use this equation with, regardless of the size of the particle. As long as it's a particle, not a photon, you can use this equation. And the proof is, well, we can calculate the wavelength for a ping pong ball. Okay, now in this case, we have that ping pong ball is 2.5 grams and is moving at a velocity of 15.6 meters per second. So what do we have here? We have that lambda is equal to h, that's constant, Planck's constant, divided by mv. Now, if we use this information, then Planck's constant is 6626 10 to the negative 34 joules times second divided by 2.5 grams times 15.6 meters over second. And then we have a problem here. We have a problem here because if you look at the units, you have joules, seconds, meters, and grams. There is nothing that you can actually cancel with here. So remember, we're calculating a wavelength. We're supposed to end up with units of length. And there is no way here that you are going to end with units of length, right? So at best, you are going to end with joules, seconds squares, grams, meters. And this is more like a soup, so you don't want that. We don't want this. So the way to work that around is one additional conversion factor that tells you that 1 joule is equal to 1 kilogram square meter over square second. And technically all you have to do is take this, put it there, and you're good to go. So that becomes now 6626 10 to the negative 34 is just 1 to 1, right? So it's kilograms square meter square second times seconds divided by This, since we have kilograms here, this has to be kilograms now, so it's 2.5 10 to the negative 3 kilograms. Okay, let's write down. Convert to kilograms. And now the meters per second can stay the same, 15.6 meters per second. So how about we check our units now? So kilograms cancel with kilograms. Seconds here cancel with one of the seconds. Seconds cancel with the other seconds here. And meters cancel with one of the meters here. So you end up with a unit of 1 meter there, right? However, the question asks for nanometers, so we need that extra step. 1 nanometer is 10 to the negative 9 meters. So these two cancel here. Now, once you are done with this calculation, you are going to obtain lambda is equal to 169 10 to the negative 23 nanometers. So if you think about this, visible light is in the order of 300, 700 nanometers. This is a really small wavelength. So if that ping pong ball was moving with wave-like behavior, this would be the wavelength. So we cannot see that. Even if it was actually moving like a wave, we wouldn't be able to see it. Okay, so but this is the wavelength associated with that ping pong ball moving at that speed. But what if it's a different particle? What is if particles such a hydrogen atom? Okay, we can do exactly the same. What do we need? So it's wavelength of the particle, in this case a hydrogen atom, h and v. So we already know mass has to be in kilograms, but you are being given grams here, so this is equal to 1.67 10 to the negative 27 kilograms, and the speed is already in meters per second, so that's good to go. So lambda is going to be 6626 10 to the negative 34. We already know we have to change the joules to kilograms, so we have kilograms meters square seconds square times seconds divided by the mass, 167 10 to the negative 27 kilograms times 475 meters per second. And everything cancels except the meters, and we need to multiply this by 1 nanometer divided by 10 to the negative 9 meters. And what we obtain here is lambda is equal to 0.835 nanometers. Now this is something that can be detected. This is something that if you were able to see the hydrogen atom, you would be able to see moving with that wavelength. Okay, but still it's in the subatomic particle world, and then we still can't really see what's going on there. I mean, in terms of looking, being able to see the particles. And that brings us to another interesting concept in atomic theory, in the modern atomic theory, that is the uncertainty principle. Okay, we already know this, right? The electrons have wave-like behavior, and we know that because we can see an interference pattern. Okay, that's a given. We already know that. We know they are already particles. How do we know they are particles? Well, they respond to magnetic fields, they respond to electrical fields. We saw that when we were exploring the early atomic theory with the cathode rays tube, right? But if we want to observe both behaviors at the same time, we just can't, okay? So if we try to see an electron, so to speak, we can't, because we are not able to gather all the information on the electron at the same time. And information like what? Okay, what speed is moving and where it's located. So to know where the electron is located, then technically you have to see it, right? And why do you see things? Because light is reflecting on the objects that you're seeing. If you are in a room and it's pitch dark, you cannot see anything. Why? Because there is no light, right? So in order to see an object, you have to put some light on it. But the electron is so small that it will absorb the energy that you are using to try to see it. So once you shine some light in the electron will disappear, technically. So we have this equation that is the Heisenberg's uncertainty principle. And technically, what you get out of this equation is that you cannot know about the position and the speed at the same time. You either know the position or you know the speed. And the more you know about the other one, the less you know about the other one. So if this is uncertainty in the position and you reduce this, remember this is an equation and they are inversely proportional. If one goes down, the other increases, right? So technically, what you get out of this equation is that if you reduce the uncertainty on the position, if you know more, I mean, uncertainty at delta x of 0, let's put it this way. Delta x equals 0, you know exactly where the particle is. Like seeing a car, okay? A car is parked, it's right in front of you, you know the car is there because you can see it. You have 0 uncertainty, okay? But if it was a 0, then you absolutely, if it was an electron, that is, if you know exactly what it is, you wouldn't know at what speed it's moving, okay? So the thing here is that if you know more about the position, if you reduce the uncertainty in the position, then it follows that you increase the uncertainty on the velocity. Likewise, if you decrease the uncertainty in the velocity, if you know at what speed the electron or that particle, small particle, is moving, then you increase the uncertainty on the position. Okay, again, the more you know about one of these, the less you know about the other. You can use this in equation. It appears rarely in the exam, but it's just like using, it's an inequality, so it's always, you're still gonna be calculating a number, but instead of saying it's equal to this, you're gonna say it's larger than this. But that's it. That's the concept with the Heisenberg uncertainty principle. It's an uncertainty principle because you cannot know the position and the speed of a particle, and a subatomic particle for that matter, at the same time. The more you know about one of them, the less you know about the other one. Okay? And that's it.